Good afternoon. I would like to thank you for the opportunity to be here and present my work on the use of the CALPHAD methodology on microalloy steels. The talk outline is a brief introduction, then we're going to discuss the thermodynamics of the carbonitrides, especially in steel, of course, and then since most times we are not really in equilibrium, we are going to discuss the methods we can use to predict or to understand what's going to happen out of equilibrium and also to have some idea of the kinetics of these processes. Finally, I hope to give you an outlook of what I expect will be the near future and how these methods can be useful. If we look back on how this knowledge we have today about this carbonitrides develop, it has developed mostly in two ways. One part related to the compounds themselves, and the other part in the relation to their solubility in steels. The compounds were studied back in the 40s, late 40s, early 50s, and you see this graph that back in 1949 it was already seen that niobium carbide, which is here CBC, and the other carbides had the full miscibility. So there's, you can see here the titanium carbide and vanadium carbide, and there was observation that the miscibility was complete. Later, very close in time, the solubility between, or the miscibility between niobium carbide and niobium nitride was observed, as well with titanium nitride and vanadium nitride. So we see that these cubic carbides were fairly miscible and in a wide range of compositions. Also interesting was that back in the 50s too, it was observed that the stoichiometry of the NBN, for instance, was not exactly 1-to-1, but it was somewhere here. This was a little bit lean in nitrogen. So this was an important observation too. Back then in the 60s, so 10 years after that, there was the first attempt at determining the solubility product of niobium nitride in steel, not niobium carbide. And this was done by Smith. And he measured the solubility of the nitride. But 3 years after that, Mori in Japan have tried to measure now the carbide solubility, and he also observed the non-stoichiometry of the carbide, and he noticed, of course, a different solubility product compared to the Smith's value for the nitride. And also he noticed that the composition was not just niobium carbide or niobium nitride, but there was miscibility between the phases or between the compounds. Then the Irvine tried to solve this or to handle this by introducing an atom-to-atom ratio here, but this is not really a good solution because you're not really taking into account the mixability of the two compounds. Further continuing on the compounds, the people at Planze did this very interesting work, and they realized that some of the carbides, like vanadium carbide and niobium carbide, had a miscibility gap at some temperatures. So the high temperature miscibility could disappear at lower temperature, and this is like a lower temperature. We're talking about 1200 C, not that low temperatures. And then in the 70s, we had this, the CALPHAD method came in. And using this, we could see that the solubility and the miscibilities of the carbides were very similar. And you can use solubility products to get phase diagrams. So this was a big breakthrough, I think, by Larry Kaufman and the CALPHAD people. Now, continuing on the same line, then in the 70s, Matt Hillert and Stephenson developed this model of the mixed compound energy formalism, and it's interesting enough, Rudy did the same some 3 years ago, and this idea was that if you have the miscibility of two compounds like titanium nitride or titanium carbide, niobium carbide, and so on, you can assume that there's mixing in different sublattices. This became a real important movement in the CALPHAD community. It was based on the mixed salt ideas. And then in 1988, Hiroshi Otani was the first to come up with the idea of having a single FCC phase. So this from the FCC phase of iron to all this carbonitride, this was also modeled with a single FCC phase. And then there was some improvement on it because the Otani's results were not really very exact, and Balasubramanian and Kirkcaldy improved the results, but not the model, of course. And then in 84, you see the situation was already very confused when Palmieri tried to summarize all the different solubility products that we had for microalloy steels. So this continues with many assessments in the CALPHAD method and much work in the solubility product arena, mostly Irvine, Turkdogan, and Palmieri. If we look at some results that were obtained with steels, we see Zur and Kirkcaldy, for instance, they measure very carefully in titanium niobium containing steels. And they showed very easily that there was really, or not very easily, but they showed very clearly that there was compositional variation depending on the temperature. So the carbides were not really titanium nitride and niobium carbide as we would like to think, which is very simple, but they were much more complex. Palmieri tried to simplify, and he calculated, he did atom probe, he measured the composition of the steels and the solubility, but then it's a little bit conflicting because he told there was no carbonitrides in his steel, but the best fitting for solubility was the carbonitride solubility product. Later on with the assessment by Karin Frisk, we see very good agreement of the compositions, and also she was able, and all this, the assessments from there on were able to describe very well the miscibility gap, for instance, here between niobium carbide, vanadium carbide, vanadium nitride, and niobium nitride. So this is the region where you have immiscibility in around 1000 or 1200 C, and these are values measured with TEM, so it's a real challenge to do this experimental measurement, but you can see the modeling works very well. Now, when you compare the values calculated by this CALPHAD methodology then with some classical solubility products, then you see, for instance, if you do it for one of the steels that Palmieri used experimentally, that the value he calculates or he proposes with this formula is quite different from the value that you calculate with the thermodynamic databases, considering that the compound is not exactly niobium carbide, but is a carbonitride. The same happens if you take Turkdogan's compound, in which he assumed a fixed stoichiometry, because this is not really happening, that you have a fixed ratio of carbon to nitrogen. And if you do this, now if you project this surface into a plane, you can see that the values for solubility are much different because there's no way you can really take in consideration the influence of varying carbon and nitrogen in the compound. So the values predicted by these simple formulas are not very accurate compared with computational thermodynamics. Now, of course, the fact is that when Turkdogan and Palmieri did this, it was not very easy to take in consideration all this data. Now the softwares are available, and you can do these calculations rather easily. So you end up doing this classical temperature versus volume fraction of phases for the steels. And if you start with the liquid, you can see the liquidus temperature, you can see the formation of ferrite, you have a peritectic reaction, then you precipitate one carbonitride, which is richer on titanium. I just simplified here, of course. Then a carbonitride that is richer on niobium, with more like a carbide, then aluminum nitride, and so on. So this gives you very easily the solubility or the precipitation temperature if you want to reheat this steel to dissolve the carbide and so on in equilibrium. Now, if you want to really look into the more complex steels like this one, which is a vanadium, niobium, titanium steel, and you take in consideration the whole composition, you see that, again, you have a first FCC phase that is a titanium carbonitride, or mostly rich in titanium. Then, at around 1100, you precipitate a niobium carbonitride. Then, at a lower temperature, you do precipitate vanadium nitride with carbon on it. So, and you actually see all these compounds when you do TEM on this steel. Interesting enough, I mean, when you try to look at the composition of this FCC phase here, you have a very strange variation. I mean, the titanium, for instance, is very high. About 90% of the metallic content in the carbonitride is titanium at the high temperatures. But when you come down in temperature, the titanium is not does not keep very high, and you have lower and lower titanium, and you have niobium and vanadium increase. Now, you may say, you probably think, well, this is very strange, because how is this titanium going to come out of the precipitate and the niobium is going to enter as it grows? So, of course, this is what would happen if you equilibrate your steel at these temperatures, and not what will happen if you process this steel at a constant speed of cooling, for instance. It's a different, altogether different thing. It gives you a very good estimate of what's going to happen, but it's not the reality. So what does the equilibrium calculation mean? It means that what you would find if there was equilibrium. So it doesn't reflect reality exactly, but it's a very, very good first guess. And also, if you're looking at the thermodynamics, I mean, there's really no sense in introducing deviations that are kinetic on the solubility products. They should be done afterwards when you're doing actually the kinetic calculations with the proper thermodynamic data. So in summary, we can say that the computational thermodynamics now can give you a very, very consistent prediction of equilibrium information of these carbonitrides of all the microalloying elements, considering not only the different compositions and temperatures in which they occur, which is already a big challenge because you have them occurring from relatively low temperatures in steels like vanadium nitride to very high temperatures for the titanium nitride. But also you can take in consideration the effect of other solutes. So you can see how manganese affects this, how carbon affects this, how silicon affects by changing the activity of carbon. So there's a whole range of information that you can get here for your alloy design that you could not get just by doing a simple solubility product. So the question, I think, is, does it still make sense to use a simplified stoichiometry, a fixed solubility product when you do your alloy design or you do your process design? So I'm not going to answer this. This stays as a question for you. Now, when you try to add this very expensive or more expensive microalloying elements in steels, you have to be careful because sometimes you have significant losses, not only in steel making, but you have losses in solidification. I mean, you can see titanium nitride precipitating as relatively large particles. You can see sometimes even niobium and vanadium being present in these particles. So one of the important things is to model what is happening during solidification so you can try to better design your alloy to avoid this. So what we do is we take the secondary arm spacing to model the segregation. And then, since DICTRA can only handle simple geometries, we sort of imagine that this interdendritic space is going to be like the center of a cylinder that is placed on this position. And so this is more or less the physical model that we're doing with diffusion. So DICTRA can only model diffusion, but it models very accurate diffusion with the proper thermodynamic data and the proper interaction of the diffusing elements. Then we go back to, this is a microprobe measurement, we go back to measuring the steels, what is the secondary arm space and with this we can derive the cooling rate. So if we do the microprobe for these two steels here that I'm taking as an example, and then we can get the secondary dendrite arm space here from this, and for this steel there was only primary dendrite arm space. And then with the Suzuki relationships or any other good relationships, we can derive the cooling rate at this position. Now with DICTRA, we can then model the segregation. And if you can see this, the blue line is the segregation as modeled from the interdendritic region, from the center of the dendrite to the interdendritic region. And the green squares are the experimental points from the microprobe. So you see that the DICTRA models fairly well the segregation, and I just choose manganese to present you here because we did all the microprobe using manganese. And you can see right away that not only the modeling is good, but also a byproduct of this modeling is that you can see that if you increase manganese and if you increase carbon, which is the case with this steel, you get much, much more segregation. It is going to be a problem for your niobium, be a problem for your titanium, which are going to also segregate when they are pushed by the liquid. So we can also use a one-dimensional or zero-dimensional model, which is just SCHEIL model, in which you assume that the elements go into the liquid and they partition and they never partition back to the solid. It's a very classical way of describing solidification. This was devised back in the 1948, I think. And then with the SCHEIL model, if we exaggerate the segregation, you can also see when these carbides or the carbonitrides start to precipitate in the solidification. So keep in mind, this is going to be large particles. They are going to be essentially niobium carbide or titanium carbonitride that is going to be lost. I mean, it's a Loing addition that is going to not to be useful for what you're going to do afterwards. And for the other steel, we also get a temperature here where this material with this precipitates form. Now, when you compare the two methods, the more sophisticated diffusion methodology with the SCHEIL methodology, we find that the temperature in which the carbonitrides precipitate is very similar, maybe 10 to 20 degrees difference. So if you're looking just at the temperature of when the precipitation is happening, it's not too bad. I mean, you can use either one. If you want to really have a better look at what's happening during the solidification, diffusion modeling is much better. So what we can do is to quantify how much microalloying we are losing to large particles, because this is never going to dissolve completely again. And then we can also evaluate how the segregation of carbon, manganese, silicon, how these guys are also influencing on our titanium and niobium losses due to segregation. So at the end of the casting process, if we have titanium additions, you can have a very dramatic situation. And of course, I put very large nitrides here so that they're easy to see, but you have nitrides which are not uniformly distributed, and they may have also niobium or vanadium in solution. And this is the classical way they look, and we are currently trying to model the effect of the oxides on the nucleation. And this was observed in Malaysian steel some long time ago, and we observed the same in high-strength low alloy steels, that some oxides are very effective in nucleating titanium nitride. This is also on a microalloyed steel now, and you see that this is the interdendritic region, and you have a lot of particles collecting here. And this is another work by our group in which you see very large titanium carbonitrides here, and you also see relatively large particles of titanium nitride in segregated regions. So this is essentially material that alloying elements that you paid for, you add to the steel, but you're not going to be able to use it because it's going to be present as large particles that are not going to dissolve afterwards. So when you go now with the plate into a plate furnace, you're looking into dissolving particles so that you can have mostly niobium and vanadium in solution. Niobium is going to have a nice effect on austenite grain size, and vanadium may precipitate afterwards. And nowadays we are also looking at titanium to precipitate at very low temperatures, like 500, 600, maybe during coiling. So it's really important to understand how much you're dissolving what. Now, one way of looking at it is just if you have your heating cycle for the plate, this is an industrial heating cycle, then you can use DICTRA or a diffusion model to calculate for different size particles how they dissolve. And then you can also do, using the same heating curve, you can calculate how much niobium, for instance, you have in solution, depending on the size of the particles. So with this information, you can actually get how much niobium you're going to have in solution to help you during rolling. And keep in mind that this is not happening at the equilibrium dissolution, because it takes a long time to dissolve if you're going to the equilibrium dissolution temperature. So normally you have to overshoot, you have to heat higher than just the equilibrium temperature. And this is just the same, but just a little animation. When you reach the equilibrium dissolution temperature, then you have some particles dissolving completely, the small ones. Then if you continue, then you have the medium ones, and then if you want to dissolve a half a micron size particle, then you need more temperature and longer time. So this is what you have to do when you design your process, you have to know what happened during solidification, what kind of carbonitride you still have in medium to large size, what is lost and what is not lost. So if you assume that half a micron is the size of carbonitride that you want to dissolve, you can fairly well design your plate heating to achieve that. Interesting enough, I mean, there was a question back some years ago whether there was diffusion in the carbonitride or not. And physically, you would believe that there's no diffusion inside the carbonitride. But we did the same, they did the calculations assuming both, and the controlling step was not the diffusion in the carbonitride. So essentially what we found was that it is not relevant whether the diffusion is happening in the carbonitride or not. Now, the most interesting thing that people do a lot of work is only on the precipitation. Of course, you can see that there's a lot of information that is essential for proper processing that is happening before the moment when you're just going to do precipitation. And then the question is, I'm going to show you, we can do a simple SCHEIL-like model in austenite that does a very nice prediction. We can do diffusion control in single particle, which I don't think I'm going to show you today. And then you can do multi-particle, different sizes, and nucleation and diffusion control, which is the latest news in the area. So I showed you this case a little bit ago. And now if you assume that there's no diffusion inside the particle, and there's perfect diffusion in austenite, you get very close to a SCHEIL model. And we did that back in 2008, and we presented it in Italy too. And so you see this phase fraction here changes. So instead of having now three different FCCs or three different compounds precipitating, you have one, and then it changes dramatically the speed of precipitation with temperature, and then we have the vanadium carbide here. So there's a big change already in the fraction of precipitates. Now, when you remember, if you recall the composition of the equilibrium carbonitride I show you. Now, if we do the same with this SCHEIL model, we have a much, much different change. I mean, we have less titanium, so this is like forming in layers. We are sort of having a layer, that initial layer that is titanium nitrogen, and then it continues and it's forming layers which are more and more rich in niobium until bang, you get to a point here where it changes to niobium carbon. And this is happening when you look at the phase diagram, which is there's a huge miscibility gap in here between the four compounds that it can form. And this is happening because you're moving from the titanium nitride until you reach the miscibility gap, and then bing, you're coming this way. And this is what you see with these nice TEM pictures, where you have a core of titanium nitride and then these caps of niobium carbide. So you can simulate that relatively easy by doing a SCHEIL model, so you can reproduce what's happening in these cases. Now, the problem with precipitation in the solid state, and that's why I'm not going to show you Dijkstra calculations, that there's multiple aspects that are needed to characterize the precipitate distribution. Reality is much more like that than a single particle, so you have to look into volume fraction, mean size, size distribution, and then you're going to have information about spacing, and also you're going to try to predict the effects. Now, what people have been doing is very classical equations in which you take the classical formula for nucleation and growth, like Dutter and Silva did. It's a very nice work, and calculate the time required to a certain volume fraction of precipitate. Now, as this goes on and on and on, the thermodynamics is here, right? This is the solubility product. As this has evolved, we got to a point where some authors are now saying that this value A, which was by Dutter and Sellers, was supposed to be a constant. Well, they say, no, this is not really a constant. I mean, this depends also on the solubility product. If it is, and then it depends also on which elements are present. So the question I want to pose is, does it make sense when this is from the theory is supposed to be independent of thermodynamics? Now you have a solubility product here too. So now, when you use classical theory for nucleation and growth, There's some very interesting models now. There's 3 or 4 softwares that do that. You take the thermodynamics, you take the diffusion data, and you take a number of experimental information like grain size, dislocation density, and so on. And then if you are able, you need to also know the interfacial energy. And then you are able to make predictions using the classical theory, but not just by hand waving, but by using really correct free energies and correct mobilities. And this is very, very promising. Now, of course, the classical theory involves driving force, interfacial energy, stress and strain, number of nucleation sites. And so the question is how sensitive the model is to these variables. And the problem is it is very, very sensitive. If you look, for instance, at the interfacial energy, all the formulas for critical radius, for the critical barrier for nucleation, they all depend on the interfacial energy. So this is the critical parameter. And unfortunately, if you look at the literature, they used to be determined by nucleation and Krog experiments. So it's kind of a real bad cycle. Now the softwares are using these broken bond models and ab initio calculations to try to solve this. If you go to the literature and you look into the interfacial energy between austenite and nitride or carbides, there's values everywhere. I mean, you can find from 0.1 to 1.5 joules per square meter. So essentially what becomes is you have a very, very sensitive model to a given parameter. Then this parameter varies immensely when people fit or measure or whatever. So it becomes a very dangerous exercise because you can almost fit anything by adjusting this little parameter. And then worse than that, you can go in the literature and say, well, when you find that it was 0.4, you say, wow, this was according to this reference. And then you say, wow, fantastic, I solved my problem. So the new softwares now, they have all models in which they calculate sigma as a function of temperature and composition. This is just a graph from Prisma that shows you that the FX from 0.51 to 0.66, how it varies at a given temperature just by varying nitrogen and carbon. So I'm going to show you just one of the adjustment when we did for niobium carbonitride with the classical work of LeBon back in 75, because this is not easy. The experimental work is very difficult to do too. So if you look at 900 degrees strain free, and we are really, I mean, all you steel makers are really interested here when you have niobium precipitation. I mean, this is temperature, this is niobium in solution. So this means that as the time goes here, you have less and less niobium in solution, so you are precipitating. And here is what's happening, how fast you precipitate when you have deformation. So what we try to do is then we adjust this to see what happens. And then if you do it with Prisma, and these are the values, so this is exactly going back, this is this curve now, niobium and austenite versus time. And if you change from 0.2, 0.3, 0.4, 0.5, 0.54, the interfacial energy, you have a huge variation in the kinetics. And the dashed line here is the value that Prisma calculates, which is fairly good agreement with the values from LeBon. But keep in mind that you're not just, when you do this, it's not just changing this one parameter, niobium solution. I mean, you're changing dramatically the number density of particles too. So if you change the volume, the interfacial energy that you're trying to fit your model, the number density changes, the size changes, everything changes. So it's very, very dangerous to go on just fitting this number like if it was a fitting parameter. Now, when you do multi-particle simulation, you have to take in account that there's increased diffusivity, maybe because of pipe diffusion. The nucleation barrier decreases because you have deformed material that has maybe higher energy. And the models cannot take in consideration the undissolved precipitates. So you have to, in principle, ignore that there is a little particle there that is going to act as a nucleus for what's going to happen. And then we don't have a model yet that can do, for instance, interphase precipitate. We can only do a single matrix. But this is already a big challenge if you're looking at the carbonitrides in austenite. So what we did was we created an effective nucleation barrier using a an adjustment in the interfacial energy. So we got some some classical results from literature about the effect of deformation on the recrystallization, on the precipitation of niobium carbonitride from various authors. And then we had the effect of the deformation on the nucleation barrier. So this now is fed back on the model, and we can do a volume fraction versus time precipitation for niobium carbide in a given steel. And we can then, if we want, we can take the 5%, and then we can do this in different scales. We can see the size of the precipitates as it moves along the time. And this is very interesting because we can also calculate how, for instance, the niobium in the solution is going to vary as time goes by and precipitation happens. So you have a lot of information that you can try to use to better understand your recrystallization. So currently we have work in progress that we are relating. For instance, this is a double deformation testing, and this is the known recrystallization temperature for the steel, for this steel, which is a classical microalloy steel. And this is the 5% precipitation curve for niobium carbonitride, which is fairly reasonable maybe. And then for a higher niobium, lower carbon manganese, we have this discrepancy. But it's very interesting because we think that this is perhaps more accurate than what we were able to do in the deformation test. So we are testing this. And of course, there's significant room for improvement. This is when you get the data from variant, and instead of just looking at the volume fraction precipitated, because this is, let's say, a real simplistic way, because you're not taking into consideration the size of the particles. Now, if we go back to Zinner's theory and we say, well, Zinner factor depends on the volume fraction divided by the particle radius. So now I can plot for 1000 degrees, which was one of the experiments they did. I can plot the Zinner force, and I say, well, there's a maximum Zinner force here to prevent grain growth, and then it starts decreasing, and it's probably not going to be able to prevent recrystallization at some point. And these are the results of Reich. I mean, it's a classical double deformation. It stops here, the recrystallization, then you have some time. And why do you have some time? It seemed like as the particles are coarsening, the Zinner factor is decreasing, and then you're having the recrystallization again. And so in summary, to not go too much over the time, I think equilibrium is now very well determined and reproducing using computational thermodynamics. So I think it's very dangerous now that we keep on using effective solubility products, including those that people say, well, this is better because this was determined in industry. Of course, it may be better if you determine for your steel in your plant, but if you're trying to use something that was empirically determined in another condition, it's going to be very difficult to be able to fit, and it's going to be probably not useful for extrapolations and for alloy design. Now, solidification model is very useful, and it's helping us a lot to evaluate what we're losing in microalloying elements, because they are not cheap. So we can probably improve alloy design, reduce additions of higher segregation elements, so that we can save on the microalloying elements. The diffusion model, the diffusion modeling we use in Dietrich, can be very useful to understand, especially the dissolution processes. This is what we've been doing, and it helped a lot to use as much as possible the niobium that we have in the steel. And then the classical nucleation and growth theory is now used coupled with computational thermodynamics. And this is a fantastic avenue to study precipitation dissolution, and I hope that in the next years we'll be able to really do some forecasting, or maybe some careful adjustment, and then developing new steels based on these models. And so I think the improvement that we are having in interfacial energy measurement and diffusion and nucleation are critical aspects now. So the question again is, should we improve our modeling by better adjustment of these empirical equations, or is it worth trying to go back to fundamentals and couple them? And all these softwares now have very easy interfaces, so you can make your model interface with thermocalc or with other softwares that we've seen before using Python or whatever. So it's a question, are we going to continue using empirical models, or can we improve a little bit? So finally, I would like to thank CBMM and my friends in the various steel makers in Brazil who have helped so much in these projects and discussing the various difficulties, and thank you very much for your audience.